Welcome to our presentation for digital circuit design. Our project's topic is logic circuits in IoT and smart devices. This work submitted by Hamraeva Yasmin and Symbat from group SIS-2309. In this presentation, we will discover how logic circuits power the intelligent devices that connect our world, enabling smart homes, wearables, and industrial automation to make decisions and communicate seamlessly. Let's start with the basics. What are logic circuits? Logic circuits are the fundamental building blocks of digital electronics. They process binary information, ones and zeros, to make decisions and perform computation based on predetermined rules. In IoT and smart devices, these circuits are what enable processors to interpret sensor data, execute algorithms, and control physical actions. Essentially, they act as a digital brain, transforming raw input from the environment into intelligent responses. This is what makes devices smart, allowing them to understand their surroundings and react accordingly. The core of all logic circuits is composed of logic gates. Let's briefly review the most essential one, the AND gate. AND gate outputs a 1 only when all of its inputs are 1. It's used for conditional logic that requires multiple conditions to be met simultaneously. The NOT gate inverts the input, turning 1 into a 0 and vice versa. It's essential for negation and signal inversion. The OR gate outputs a 1 when at least one input is a 1. This enables alternative pathways and flexible decisions making. The XOR gate outputs a 1 only when its inputs are different. This is critical for a comparison operation and basic arithmetic functions. All the complex systems we will discuss are built from these basic building blocks. So now let's look at how these circuits actually function inside a smart device. Their operation can be broken down into two key stages. The first stage is sensor processing. Logic circuits receive a signal from various sensors, like those for temperature, motion, light, and humidity. They convert this real-world analog data into digital information that the device can understand and act upon. The second stage is decision making. Here, the circuits evaluate conditions using logic gates. For example, if the temperature exceeds a set threshold and the humidity is low, then the device triggers an action like turning on a fan or sending an alert to the user. This is how abstract logic is translated into tangible physical outcomes. Let's solidify this with some real-world applications. So the first is smart thermostats. Inside them, logic circuits continuously compare the current room temperature with the user's desired settings. Based on inputs from multiple sensors and preset schedules, they activate the heating or cooling system efficiently. So this is very useful. Second, wearable devices like fitness trackers. They use logic circuits to process data from accelerometers and heart rate sensors in real time, calculating metrics like step count, calories burned, and sleep patterns. And finally, industrial automation. Here, logic circuits coordinate complex manufacturing processes. constantly monitor equipment status, and instantly trigger alerts if any operating parameters deviate from the norm, ensuring both safety and efficiency. Now, Symbat, your turn.
Combinational and sequential logic, there are two main types of logic circuits. Combinational logic, the output depends only on the current inputs. It has no memory. Think of simple calculations. Sequential logic, the output depends on both current inputs and the past states. It has memory. This always device to remember things like how long a light has been on and integrational levels and the complexity. Large circuits can be very small or incredibly complex. Small scale basic circuits with just a few gadgets, medium scale more complex, use it in sensor interface. Large scale in microprocessors that are the brain of smart device. Very large scale modern processor with billions of transistors use it for advanced tasks like oh, design. Designing these circuits for IoT is not easy. The main challenges are power consumption. IoT devices often use batteries, so the circuits must be very energy efficient. Heat dissipation. Complex circuits generate heat that must be managed. Signal integrate, we must project the data from noise and errors. Security, we need to protect the hardware from hacking. Future, future trends. The future of logic circuits in IoT exciting. Each computing, more processing will happen on the device itself, making it faster. AI integration circuits will have special parts, more machine learning, right inside the device. Hardware security. Security features will be built directly into the chips. Energy device will power using light of so they never need new batteries. Conclusion Conclusion logic circuits are the assembly of our connected world. From simple gadgets to powerful process, they turn data into intelligent actions. As IoT grows, making these circuits better, faster, more efficient, and more secure is the key to smart future. Understanding logic circuits mean understanding the foundation of the future.
Thank you, Sambat. And also, I wanted to add that the logic circuits are far more than just abstract components on a silicon wafer. They are the fundamental enablers of the intelligent, connected world we live in. As IoT devices continue to become more deeply embedded in our homes, our workplaces, and our industries, the role of efficient, secure, and powerful logic circuits will only grow more critical. The future belongs to devices that are not just connected but are truly intelligent, able to make real time decisions at the edge, learn from their environment, and operate autonomously. And this future is built gate by gate on the foundation of digital logic. So, thank you for your attention. We're now happy to answer any questions if you may have them.